Evening, wherever you're joining us from. I know we've got registrations from all over the world. Welcome to this webinar presentation looking at AI production readiness for oil and gas, how to achieve greater operational excellence through the power of AI from raw data to live production. We've got a couple of great presenters today, but before we start, just go through a couple of housekeeping matters. If you want to ask questions during the presentation, please use the Q&A function at the bottom of your screen, and we'll get to those questions at the end of the presentation. For those of you who want to watch it back at a later point, so you don't have to take notes during this, if you want to refer back to it or forward it to a colleague, we will send out the recording after the webinar this afternoon. So we'll send that out to you. A lot of people like to rewatch them, and also a number of people can't watch it live given time zones, so that recording will be sent out. And we'll give the contact details of Henry and Roberto in that email to contact them afterwards. And that's really it. So I'm going to introduce the two panelists today, the two presenters. Firstly, Mr. Henry Gao, who's the head of product marketing for Petuum. Prior to joining Petuum, he held various management positions within the technology space in such companies as VMware, Cisco, and others. He's worked extensively across multiple high-tech sectors, including AI, cloud computing, virtual machines, and cybersecurity. And joining Henry will be Dr. Roberto Linares, AI Solutions Principal at Petuum. He is a customer advisor on the use of Petuum's artificial intelligence machine learning technology in process industries, specifically in the application of intelligence-based advanced process control and real-time optimization. Previously, Roberto served as the VP at PIMSoft for 9 years, where he managed solution sales in different areas such as refining, LNG, petrochemicals, metals, and mining. So I'll hand it over to Henry and Roberto now to start the presentation.
Thank you so much, Simon. Well, thanks for being here. So this is the agenda today. We're going to do a quick round of introductions about Petuum, who we are, and then go over, what do we approach AI and the way that industrial AI works. And then we'll go over into the applications that we currently see for the use cases in the oil and gas space. And then finally, Roberto will go over in detail, how do you actually get this production? What are the 6 major challenges? And what are the solutions we've seen that really works? And then I will cover some of the real world case studies we've seen. And finally, we'll give a short product showcase of our Petuum Industrial AI Optimum. So I want to start off here with, what is artificial intelligence and machine learning? The reason why we talk about here is we talk to many customers. Some are at the more advanced age where they have a very strong team of machine learning data scientists. Others maybe just getting into it. I just want to at least put into our mind and everybody else here, what is we're talking about when we say AI or artificial intelligence? I think Gartner captures the essence quite well. What they're saying is applies advanced analytics, logic-based techniques. Doesn't have to use machine learning. Most of the current methodology does. And then what it does is then it's all about supporting decisions, taking inputs, outputs, interpreting events, and and automating this and having as best outcome as possible. So the way we approach it is at Petuum, very similarly, many of us start off in the computer science field, and we have a lot of great team members from machine learning, AI field. AI encompasses is a part of computer science. Underneath that is machine learning, and below that is another technique, deep learning, where a lot of times you're hearing with neural networks, backtrack, all these other ones. We apply all this throughout our product to the customer. So, the summary of this is AI is not magic, right? It's a science. It's based upon principles of logic, based upon mathematics, statistics, and computer science. And the methodology you can do it is using deep learning or applied machine learning, which we'll go over in detail today. Who we are, so we're founded back in 2016, really backed by tier 1 venture capital and other firms. And what our founder is, Dr. Eric Xing, was a top AI researcher. He's a professor at Carnegie Mellon University, and our co-founder and one of his star students, Dr. Chirong Ho, founded a way to do applied AI. And that's what's the genesis of the company. And we have around 50 plus people from Carnegie Mellon, MIT, and so on, PhDs and masters from this space. So our DNA really is this idea of using cutting edge research of AI and really solving really tough real world problems, which will showcase how we approach that today. And Petuum really kind of has three major components. One, the ML infrastructure backend. Really, this is the glue that makes us able to build products faster. It's really the system ML piece, the researcher Dr. Ed Xing and Dr. Qirong Ho built off of. It allows us to have scalable AI. We can actually do distributed training faster. We can do automated. We have backend systems allows us to quickly automate it. Composable, where you build off of UIs and different ways to match that. And that's why we're able to build these cutting edge AI modules. So these modules will cover things from decision systems, taking data points, understanding how do you apply that, computer vision, where we look into different images, videos, understanding, segmenting it out, and then figuring out what is the individual pieces. And then finally, natural language processing generation, actually understanding text, semantic search, summarization. So each of these components or modules is able to modularly added and edited by our team. So that's why we're able to quickly build these product lines. Really, our flagship is the industrial AI, where we cover how that works for the oil and gas space. Blink Label is where we're doing working with self-driving cars, drones to do computer vision, and then our AI writer is doing the natural language processing component. And each of these different ones builds on top of the lower component, so we can actually get this faster and able to modular out. And really, how we approach this today is a lot of our customers have good operations. They're operating at a fairly robust phase. They look taking into a lot of considerations, maximum pressure, flow rate. They have this zone. But what we are doing is we're actually applying machine learning and AI to this to push out that component, to really further out, to get closer to the constraints. So the customers are not just working on the comfort zone, but actually getting that excess improvement yield, stability, and everything else. And the way we approach this is there's really 4 steps. Is one, we looked into work with our customers, understand correlations. What's some kind of simple correlations we can see? That's the first step. So we understand what the historical data, what are the tags, what do they want and trying to actually see. From there, we can actually predict out. We can do it 5 minutes, hour, 2 hours, even on low frequency data inputs, doing soft sensors. A lot of things we've seen with different customers. So we can predict this out, smooth out any of the other outliers, any broken sensors, and actually understand what's going to happen within the time frame that's given. And once that does, we apply multiple models and have these what's called prescriptions, with optimization points. This is where we tell operators, if you input or control these other variables, you could actually can get closer to that optimal optimal operating procedures as much as possible. And finally, we call supervised autonomous steer, is when we actually write back to the control system when customers are ready and our AI is actually running a production line or another fractionation or some type of different components within the manufacturing process. So many of our customers, depending on where they are, will get to from correlations, predictions, prescriptions, and then we'll work with them if supervised steer makes sense. But there's always an operator in the control to make sure everything's running the way it should be. So I covered in general, really quickly, kind of the components of Petuum. And the 3 ones I cover is computer vision, natural language processing, and decision systems. And each of this is applied throughout multiple product lines. I'm going to hand over to my colleague Roberto to kind of go over a little bit in detail the different use cases for oil and gas.
Thank you, Henry. Yes. Yeah, so if we see in the automation technology of oil and gas, there are certain layers for this control of the complete, let's say, refinery or plant. At the very bottom, right, we have the regulatory controls, the advanced regulatory controls. On top of that, we can do optimization, the optimization with APC, advanced process control. This advanced process control might use some soft sensors or advanced soft sensors. Then on top of that, APC, you might have a coordination of the different APCs in order to get the best out of the combinations of the operations of those units. And then, in the very high level, we have the linear programming, where we use the prices and different technologies in order to get what is the best flow rate to run the plant at for the different units, etc. AI can be applied in any of these layers. Um, However, we will be talking a little bit more about the three layers in the middle, from the sub-sensors, or also called inferentials, the APCs, and the RTO. And we will see a couple of examples. Yeah, so typically in a refinery or chemical plant, a petrochemical plant, there are places where you have reactions, you have the reactors, you have separation units, or you might have a collection of all of those in a complete process, right? So if we look at the essence of these processes, let's say that you have a reactor and you want to apply machine learning and AI. So first of all, you need to define the objectives. What do you want to do with this reactor? You want to have more throughput. You want to increase the selectivity. You want to have, let's say, longer life of your catalyst. That could be some of the objectives, or it could be multiple objectives. Then you need to describe, okay, what are the constraints of this process? You want to run a certain maximum temperature, certain pressure ranges. Um, for that, we first create a prediction model, right? So, how do we build this model? Okay, this model is data driven. So let's say that we have 100, 200, 300 pieces of information and tags, tag names. We get data from the process data historian. We might take, let's say, 1, 2, 3 years of data. Then we build a dynamic model. So this dynamic model could be different types of architectures of neural networks, different models. I mean, that's basically our machine learning engineers find the optimal pipeline, machine learning pipeline, in order to do the feature extraction, understand the correlations, create a dynamic model so that we are able to predict accurately in the future what these goals are for each of the inputs and what these constraints are for the inputs. So once we predict well, and when we mean prediction, is that we can compare the measure values versus the values that are coming out of the AI ML model, then we know that we understand the process dynamically. Of course, that we also validate the input and outputs expected answers from the model based on first principles. So let's say energy balance, or uh, knowledge of the operators, knowledge of the engineers. So that prediction phase probably is the most challenging one, right? So once we pass that phase, then we can prescribe. We can build a dynamic optimization um, where we can track the different trajectories and find the optimum trajectory to go from one state to the other one. What will be the optimal moves so that we can go from state 1 to state 2 and so on as we control the process. Initially, the system can be used in supervisory mode, where operators can take a look at these the prescriptions, try them. Once we have the validation, we can go to complete closed loop control of the process. Yeah. So we have other use cases. For example, here in the next slide, we will see a distillation optimization example. Um, we have cases where we have the different distillation units or group of distillation units, but here we can see one of the, in as a single item, can we optimize a distillation column? Yes, we can. These are processes that have some delays, right? And you have a group of these together, and you want to optimize all of them. You need to consider the long time delay that happens when you change, let's say, feed, or a disturbance happens when that is going to take across the whole process. So, taking the same methodology, basically, again, we define what we want to do. We want to, let's say, maximize feed, or we want to have more stability. We want to operate closer to the constraints. Let's say we want to minimize the giveaway, or we want to keep product within certain constraints. And then we can keep all of the constraints that we want. We can add more disturbances variables. I mean, this could be hundreds of variables in a model. So that's part of the definition. Again, we build a dynamic model. We have experience of finding the correct machine learning model that is going to give you very accurate, according to the metrics, different metrics that we have to say, hey, yes, we have a good model that can predict, prescribe, and then that can operate optimally according to the objectives of the customer. Could we go to next? Yeah. So now, in terms of plant optimization, other people call this RTO, and this is again based on AI, I mean, and ML. In this case, we are grabbing data, from, let's say, 3 complete units with all of their ancillary equipment. We can build a model, right? That we will build a model again, but in this case, we are looking at all of the different units working together. We might take 1-2 years of data again. For example, in this case, let's say that we want to find for 2 or 3 units or 4 units, what will be the optimum combination of this operation, considering the individual constraints of the process. So here, just to simplify, I have selected a few, let's say, objectives, right? So maximize overall throughput, right, or maintain throughput for the whole units. And then we want to get to a certain specification of product, and it could be the mixture of the product. So in a way, you can have a little bit more giveaway in one and less in the other one in order to be able to satisfy the whole thing and do the optimum. So then we need to see what are the individual constraints, what maximum flow rates, maximum, let's say, valve positions, monitor of that. And then we can prescribe optimally what will be, let's say, feed rate for each one at each time. What is the actual temperature that you need to be running the different units, reactors or separation units, and then finally to have a complete closed loop control. Of course, this is the frequency is not as high as you might expect, right? So these moves are, let's say, done more in the 10, 20, 30 minutes compared to the APC models. Could we go to next? Yeah. So, also AI has the ability to look at other types of data, not only numerical information, like we see in, say, process data historians. Now there are cameras, there are pictures, video. Some of these could be thermographic images of equipment that are operating at high temperatures. There are also the flares. All of that information can be used to monitor the process, to detect issues. Let's say that you have a problem with insulation, right? You can teach, of course, a machine with ML AI in order to detect the issues of leaks, high temperature problems, on, let's say, a problem with the formation, let's say of a flare. Let's say that there is a pattern that is showing there is an issue, right? So all of those things can be looked at as data, right? So we can have. It's very difficult for a human being just to be looking at a monitor all the time. So this can be built. These modules can be configured in order to grab information for operators and engineers as well. Yes, good. Yeah, so. Yes, and now we will see, what it takes to go from data to a model that is operating in a closed control loop, and we will just share with you some of the interesting things that happen when you develop this system. So, there are some challenges, and of course, in order to face those challenges, you need to have a backend platform. We have our own backend system that allows us to do many things, like processing data, validating the model, facing any of the delays of the process, work with the experts in order to configure the system so that we work in a coordinated manner with existing controls, take care of inferentials and develop inferentials, and then being able to keep these systems alive through adaptive learning and improvements of the process. So in terms of data processing, right? When we receive, let's say, 2 years of data, then you need to automatically being able to remove spikes, remove periods of downtime. You need to remove outliers, check there are on stationary signals. If there are some broken sensors, abstract information, get information from the valid periods, and being able to identify when let's say when the system is not working, perform smoothing interpolation in the pipeline, right? So the important thing is to being able to provide the information that the MLAI model needs to learn, right? If the data doesn't show it, the AI cannot learn something that is not shown in data. So we can go to a second challenge. Something that we do is that for every variable that we are trying to predict for all of the outputs and constraints and goals, we all the time are checking, what is the accuracy of our prediction, what is the expected, gain. If we go to let's say a steady state, being able to see if our neural network is able to capture the delays, the final gain, so that we know that we can, we are not just showing a nice graph, but it's a nice, it is really an algorithm that can control the process. And then we validate these behaviors, these input and output behaviors from state from one state to another, uh, with the APC engineers and experts, just to be sure that that the system will make the right decision when it's moving, let's say, a position of a valve, or is increasing, let's say, a temperature, if it's going in the right direction. Yeah. So also something that is important is the long process delays, and for that, I think the important thing is to have the correct machine learning algorithm that that will capture. Let's say you have a process that takes 3 hours to settle, 2 hours to settle. We need to be able to predict in that long time horizons, right? So we need to be able to detect malfunctioning, and also use values that we can use inferentials, or we can use typical values. So all of those decisions need to be made in order to have a good model that again will be able to track and predict, so that when we control, we're not just looking at 1 minute from now. Because as we know, let's say that we have a series of equipment, it could be that we will face an issue in 1 hour, but if we don't predict 2 hours ahead, we won't be able to see it when we do the optimization. So yeah, and this is really, I think, important. If you develop an APC application, we need to be, we need to respect whatever control loops already exist there as a regulatory control, right? If we are going to be we don't want to, bypass, let's say, a PNID, for example, right? So we need to be sure of what we can manipulate and what we can have in the constraints, so that we avoid an issue at the lower level. So in the case of if we are using we're developing RTO, is the same thing. We need to be able to to determine what are the things that are going to be manipulated at the level, what are the things that we will be controlling and monitoring. So this is probably more like a engineering effort, and this is a part of the conversation with the APC engineers of the plant. Yes, yeah, and something that is really powerful now is the the use of low frequency data, right? Many of these products take a long time to get the sample, then you go to the lab, then the testing takes some time. So at the end of the day, you don't have a lot of data, and the frequency is not that high. But that's not a problem, because We can use different techniques, like time averaging across around the sampling time, finding, there are multiple things that we do in order to understand the lags of inputs and outputs. And then the important thing is being able to find what will be the best machine learning method that is going to predict best that specific property, is either that composition or is any other physical property that we want to control. And then for that, we can use the decision trees, random forest or linear method. So, everything has to be evaluated to see what will be, the best for the specific application. If we just want to infer a value, if we want to explain why, probably some are better than others. So that's also engineering judgment that is used as well. So if we go to next one. Something that I would say is really important is that, once you have a deploy system, let's say that you have now 2 or 3 months of more of data, right? So let's say that we have some changes in the process, some process fouling, heat exchangers. Now there is a little bit of a change of behavior. So in reality, as we collect the data, we can just retrain the system, and the system will adjust automatically to the new parameters. So that's very valuable. The other thing is this, that we are using very complex models that can handle very well the different states. So what I mean is that we are not linearizing anything. So let's say if a linear system, let's say, is operating, your plant is linearized at 90% of capacity, now you're operating at 70 because of COVID. It's probably true that your linear system is not going to behave as well at that capacity, but an ML system can capture that very well. And also something that is very powerful is that we can capture the dynamics without doing a disturbance, or what is called bump test. So we can get those signatures automatically without that. So that's very powerful. So the redeployment of the systems is really easier, compared with, let's say, older technology. And this is the recipe to get from data, right, to an industrial AI deploy solution. So first, you start with your source of data. It could be process data historian. It could be any other system that has the data that you're going to consume to build that model. Then we collect the information. We segregate values of the information between inputs, output constraints. And we can use again control nomenclature like MB, DBs, CVs, etc. We have that tool to create this schema, and then from that we go to an AI algorithm or algorithms that will match better the prediction, right, of the process, right? So there are processes that are inherently fast, others are slow, other a combination, some part could be fast and others slow. So the algorithm is developed. Then there is a part of refinement when we look at every important, let's say, control variable versus its main prescription, right? To see if the behavior that we are seeing in the data is what the APC engineer expects. If that doesn't happen, then we can always revisit the data, find if there are some outliers, or we might be using their incorrect, let's say, tag. Then later we operationalize the system, and this means to have it now in real time, streaming, reading the data, producing the prescriptions. Then the last part is just to support it, to continue to have it. As more data comes in, we can always we're gonna just retrain and have the, like an evergreen product, providing the value for our customers.
Thank you, Roberto. Yeah, so Dr. Roberto just described in general what we typically see from our customers. I think just to reiterate some points is Petuum's built a tool for each of this. So the ACE is called AI Configuration Enablement Tool. Is we understand all the different elements of tags. We can actually build in logic in there that helps clean up, so we can do that rapid turnaround. And then with the AI algorithms, which once again is our underlining back-end system that can clean the data, understand it. And that's why our ML engineers or machine learning engineers can actually quickly understand that, build these models, validate it. And the component here is we need to also work with the customers on generally what's the refinement, the guardrails, and then on our back end, we can do it a modular on SaaS or on premise if need be to actually operationalize it rapidly. So I'm going to cover next section just 3 case studies we have seen success. So we talked a little bit about here is we enabled a smart factory manufacturing for a fractionation component. We really improved the overall yield and different elements. And the challenges is just a lot of the fragmented data that's coming in. Once again, very, very many tags, very, very different things from valves, from fans, from very different multiple factors. So the understanding is many of their previous, our customers' previous work involved linearity. How do you do this if we think about looking past maybe 6 months, 2 years? Linearly, if you go at this slope, what would happen? And we took a very different approach. We cleaned up the data, understood what are the most important factors, and built this multilinear model that's multi-layered that covers everything from pressure, concentration, and build these constraints so that it stays within this bound. And that's something we really adhere to and work very close to our customers is. We are not just building AI models that optimize, but optimize within the constraints and actually satisfy other goals and sustainability components. So we're actually building, making smooth it out. So we're not just always, hey, and anybody can do a max min-max model, but how do you actually do it in a way that tracks predictions, tracks the flow across time? And that's the complexity comes in. And like I said, the 3 ways we've done this is we predicted out. So we understand what is going to happen within a certain time frame. And then we prescribe. We build multiple models, looking at optimization, looking at very different advanced methodologies and multiple models actually for different components. And actually, this then are the different valves, the different components you turn on, turn off to hit that optimal point. So we have that. I'll showcase a little bit to everybody here how an operator will see, and then the dashboards he or she will be managing or able to witness to give that prescriptions. And finally, customers are ready is the supervised steer when we go back and talk into the control system. So our algorithms actually running these components. And the end result of this, we saw a drastic increase in yield and improvement. So previously they were getting a certain amount. Now we saw a 10, 15% depending on factors and that increase in yield. And then the reduction what I talked about earlier, the variability. So before, they will have very high temperature, very low temperatures with different components of concentration in the product mix. We able to cut that down by quite a bit. So the customers knows it smooths out the curve. They understand the actual components and keep it within the optimal bounds as long as it's safety. And then as Dr. Ruperto mentioned earlier, is we lower the production giveaway. So that way we can actually save on the components, both input and output. Another piece I want to cover here is one of our other customers in the metals and mining space is we talked a lot, and most of our work is in the what's called structured data or the time series. But we also work many times applying our computer vision technology to other means. So one of our customers looked into how do you actually understand defects? So where they're doing hot roll steel and then having production out. And a camera is capturing about 1,000 images per 10 minutes. So lots of images. How do you actually see defects? And how do you make sure you correct those? So a very quality assurance type of scenario. And our backend system is able to take all these input of images and segment it out. So one of our other technology is called segmentation or panoptic segmentation is we can actually break down the images into different components. We can say this is a steel, this is a backend, this is what a different type of defect can be. So what we did is build these algorithms on top of our backend, wrapped around it, and shipped it to our customers. And the end result is among the 18 major defects, we're able to have 98% accuracy. So we understand where the major cracks are. The minor defects is maybe where there's blemishes and other issues. we are roughly about 95% accuracy versus the operators who were roughly around 80% when we talk to the customer. So in general, by implementing this, we're able to save quite a bit of time. And a lot of the operators then can actually go into their other parts of the day job. So application of computer vision in this component saves both time and actually the overall quality. So if anything gets identified, we can capture that very, very quickly and send it back as alert from our system to an operator or for the manufacturer to quickly actually change any of the errors that's happening. And one other thing is in metal mining space, this is a very kind of hazardous, very dangerous place. So it's actually not easy for a person to be there. So this very high temperature place is a perfect application for the computer vision to doing this panoptic or semantic segmentation and actually identifying these defects. So other case scenarios, for folks on call today, any other non-trivial dangerous places, the application of digital machinery, IoT capture, and the application of computer vision ML is actually a very great use case. And finally, slightly a little bit different, but why we talked about here, I think Dr. Roberto talked a little bit about the scheduling and the corporate structure component, is this idea of logistical components and optimization. So we're working very, very closely with a airport within the East Asia space and understanding what is happening in terms of the optimization. So the case scenario is the customer runs an airport, they have multiple gates, and they have multiple airlines. This is a different scenario where customers fly in and different, how do you optimize the landing of the gates and the passengers into different and optimal lines so they don't have to wait, they don't have to travel as much, and the gates for the airport are always being used. So there is less downtime. So that was the use case. We worked very closely with the customers. We got the understanding of the foot traffic and airplane traffic of the customers, and then looked into how do we bound this problem? How do we then put it into a machine learning, deep learning problem and do neural network backend propagation to figure out this problem? And we also used simulators as well to capture some of the nuances. So from all this, we're able then to have a component where we then optimize this across different realms and actually able to increase overall traffic and also downtime for usage of gates. Finally, I want to pause here and I'll show a quick video. This is what an operator would see. So on the left side is one of our initial versions. This will be what an operator will be able to see in the terms of different variables. So the control variables here is really the control, the goals that an operator will set. Then the manipulated variables were the prescriptions that we tell you an operator to, hey, this is what you should change. And right here, you can't really see very well, but the differences in operator status versus optimum or our supervised steer running. And finally, the disturbance variable or the inputs that sets us apart. On the right is, so an operators will be able to see this, manipulate this, and actually control their systems from it. On the right is the dashboards they can double click in. On the top right will be a demonstrative of what would they would typically see in terms of this is forecasted, this is what's actually happening. And the bottom left is actually a capture of the underlying system health. So they can see in terms of our hosted system, what's the capacity, what's the unit. So if this is a Dockers or Kubernetes, they can add more resources, or a virtual machine as well. You can then add more resources to it and do this workload balancing across different realms. So I'll just show a quick video as I talk through this. So a typical operator will then go and see this control variable, set the different goals, and actually enable different statuses here. He or she will be able to set the limits and actually monitor what the value is across this time. Then they will go in and manipulate the manipulative variables where they can actually set the different constraints. We're talking about feed flow rates, reflux for the condensers, and other reboiler, different type of components, so different assets. And then finally, the disturbances, which it's about the inputs. So the steam temperature, the feed composition, how is it? Is it good and bad? So we actually have that status. Once that's ready, they can transition to an actual dashboard view where they can actually see across time what the different real-time forecasted and what the optimal level should be, and actually seeing if this this asset is being turned on, engaged, or it's not. So they can monitor that, and then they can actually turn on and off the supervised steer mode as well, depending on. And then, so you can actually then go and double click and figure out actually into a tighter time frame. So maybe you're looking at a month, you can focus on that. And then this is the, like I said, the IOPS, the input output, the different capacity for storage. You can monitor what's happening to see all that. So we have both the operator view, the dashboards, they will cover most of theirs, and also the way to see the underlying health of the system. So I'll stop here. That concludes our presentation for today. So I think there's a couple of questions Roberto, Dr. Roberto, myself will happily answer right now. So if any questions, post this meeting, please reach out to us at business@petuum.com. So I mean, should we cover the questions?
Yeah. Absolutely. Thanks, guys. Just a quick question at the start. Where are you guys based? Where's the company based?
Right. That's a great question. So we are headquarters in Pittsburgh and Sunnyvale. So like I said earlier, one of our founders and chairman is Dr. Eric Xing, and he's based in Carnegie Mellon University. And our foundation is in Pittsburgh, but we are a global company. So we also have another major office in Sunnyvale. We have quite a few folks in Texas and Montana as well. So fairly dispersed, but most of our offices in Sunnyvale and California and Pittsburgh, Pennsylvania, in the United States.
Okay. Another question, how much time do you need to do a proof of concept?
Right, that's a good question. We actually have a package called the Pathfinder. It's really for initial customers where they get on board and actually start off with our system. Roberto, I mean, roughly, I think we were able to do it within about, depending on just for correlations, very rapidly, 2 weeks. Anything further, we're talking about 5 or 6 weeks. Is that correct?
Yeah. Typically, we start with that Pathfinder, and if we want to do, let's say, correlation analysis, then input and output response, predictions, validation, and the control, then we are taking 6-7 weeks, depending on the complexity of the asset.
Okay. How can you train the model to predict upsets if it was trained only on a steady state? In a steady state?
That's a very good question. And we are not training in steady state. We are training on all of the states. We are using all of the data on steady and steady. And then from there, that's very powerful that we can derive the steady states. So we are not, for sure, we are on a steady state training, and the model is completely dynamic. That's a big difference of a steady state type of linear model.
Robert, can you cover a little bit? I think you talked about it, but some of our current customers with the COVID, I mean, seeing the change in terms of, pre-COVID is their steady state one thing, and post right now?
Well, we have seen it with different customers and even in different industries where you have a model that was designed with certain steady state, right, in mind. Then when you are outside of that point, now your model, it's not performing as well. It could be performing, but it's not as efficient. We have seen that, and that is because we are looking at the complete state space of all of this data, and also we are looking at the dynamic behavior on the relationship of the variables. That's key here, and that's a big difference.
Are you using dynamic process simulation to teach the AI model?
No, we are not doing it, but it can be done for sure. We can. The thing is this: in reality, that can be used for validation, but we also do automatic validation using conservation principles. But the simulation can be used to, let's say, validate some gains. It's not, we're not against simulator. Simulator is if it is in place. What we have seen is this, that in reality, the plant will be much more complex than what the simulator is telling you, and building the simulator with all of the, let's say, advanced control, or with all of the regulatory control, it's going to be so time consuming. So I mean, we need to think about that when we are doing it, but it's totally possible, I will say.
Okay. What is the difference between what you guys do and what C3 does, C3 AI?
Okay, well, the thing is this: we are we are going in a direction where we are advancing APC and RTO to a higher level using deep learning. Of course, that we can also work as a generic AI company that is developing, let's say, systems based on AI, ML for different applications. So, but in reality, our difference probably is the depth that where we are going to advanced process control and RTO in many process industries.
And I want to comment here is, I mean, I have great respect to C3. I have friends and colleagues there too as well. You know, they come from, their background is Tom Siebel from, and then we actually have folks from there. So, you know, their background is that element, and they came from the kind of energy trading component. And their approach is very much, you know, they brought Baker Hughes component, understanding that component, but their ways of dealing with unstructured data. So computer vision is one thing I haven't heard too much of from them. And their system, you know, they have a very C3 way of doing it, where ours is, once again, you know, with the type of talent we have, our Petuum, we approach it at every component, every customer very dynamically understanding what their constraints are versus kind of applying the C3 system. So there's some overlap, but in general, what we've seen is we have a little bit more complexity in the approach to solving this.
Okay. Is the prediction/correlation analysis solely based on historical data, or is there a bottom-up approach based on design data, reaction chemistry, LP, etc., or both?
Well, okay, that's an excellent question. And in reality, we look at data, but this data is compared to whatever information is available in the, let's say, in design, let's say. But that doesn't mean that we can drive with the design, because it could be that the plant is not operating at the design anymore. But we use it to validate what the system has learned. Now, if there are other things that the system has to learn that is based on conservation principles, let's say, I mean, we can add that to the loss function. So when we are training, that correlation is kind of reinforced. But you know, so it's not an easy answer. But I would say that we want to be our model to be what the data says it is. It's not what we believe it is, because is the plant is what the operator is doing is looking at data. They, you know, so of course the engineer will validate. If I move this, let's say I open the steam, I expect more temperature. If I see something different, then there's something wrong with the data, right? So, but it's more information is always valuable, but it has to be used in the correct form so that we don't tamper with the AI model, right? So that's I would say that. Mm-hmm.
Okay, so a question from the same gentleman, Roger. What happens when parameters go outside those that we used when the model was created? Does it alert the operator, I don't know where I'm going?
Well, no, the thing is this, that's a very good thing. And then for that, we can keep, you know, we keep safeguards for the normal operation of the system. Then at that point, we can send a flag saying we request to turn off the automatic steer, right? So let's say that you are in a startup, you know, we have not trained the system to do a startup, right? Or we have a high offset of certain kind, then at that time we can find that we are outside of limits, and all of that can be configured for sure. Mm-hmm.
Yeah, so one thing that Roberto mentioned is that constraint. So we give this optimal level, but we also set tight constraints. If anything approaches that, we'll set up a alert and keep for any of the operators. So you're at a certain capacity, you know, we will definitely make sure, you know, we have these guardrails built. That's one thing that, you know, it's very, very important to us as well.
Mm-hmm.
For the vision AI use case, where is the training done? Is it cloud or edge?
Cloud today. We do inferences at the edge, but the training happens at either a central location, or currently we're doing it on the cloud.
Okay, a couple of questions from Bosun. Can you give a quick talk between Petuum and the HYSYS digital twin?
Well, I would say that we are, well, right now we are not building really a digital twin. We're creating dynamic models to solve a problem, or static or dynamic. In this case of APC and RTO is dynamic. Now the system is really capturing all of the dynamics that has learned. That could be exposed in other ways. If that can serve in some form to a digital twin, I mean, that's for sure information available. And if that is an opportunity that a customer wants to explore, yes. But like I said, we are not. That's my point of view, Henry. What is your feeling?
No, that's a good point. I mean, we work with companies who do build digital twins. Our DNA and our company is about the what we talked about earlier, the computer science, the machine learning, the deep learning component. You know, we have our own platform and data processing software on top of that. But you know, digital twin is companies we would typically work with versus trying to go head to head with.
Okay. So Bo says you are not a simulator. You use the plant data and take the equipment behavior as a black box, predict the behavior based on the historical data trends. Is that correct?
Mostly, but we like to do explainable. So we do actually show not just beyond dashboard, but actually our system actually go in, you can see what the machine's learning looking like, what is the R2 value, what's the variable components, how is this happening? So black box is one thing we understand a lot of customers don't like, and we, as well as computer scientists and machine learning users, are all about kind of building this transparency and explainability. But in general, we take mostly historical data, but to Roberto's point, we also work with streaming as well.
Okay. Are you focused on certain market segments, or are you open to wider businesses?
It's a very broad question. Like I said, we are mostly focused on oil and gas, metals and mining, and chemical space within industrial. And our separate product is self-driving and drones.
How easy is it to integrate your platform into our existing pipeline infrastructure, etc.? Can it be offered via API?
Yes, we can be offered API. We actually have an API, robust API gateway. We're working with quite a few of our customers in that space. But once again, we need to understand the context, because training inferences is different. We will need to understand, we probably need to do some we need to tune our models to train for the customer. But once that's ready and they want to subsume it through API, we can do that.
Okay. All right. Well, there's no other questions there. I think you covered everything. Do you have any final comments? Your contact details are on the slide on the screen. So if anyone wants to contact you, business@petuum.com.
Yes. Well, thank you, Simon. No, this is really great, and I appreciate everybody here, and hopefully you guys learned a little bit. You know, we wanted to also open this more into what we've seen and how do you actually get from just, hey, you know, we hear about AI, but how do you get that from that data element to actually full-blown operations? So hopefully we're able to cover that today. Dr. Roberto, any kind of final thoughts?
No, I appreciate the times of everybody. The questions were very nice. I mean, if there are more questions, we are very happy to have a conversation, right? To go deeper in any of the subjects, and it could be APC, right? It could be about ML for control, and NLP, vision. You know, so we are, we are here to help you.
Great. Actually, there's one last question. How quickly can we go from idea to production level application?
I will say I would say it's very fast because of the platform capabilities. Some of our customers have been very impressed, right? And of course, you need to go and do the Pathfinder, the steps. However, I mean, something that is important is scalability. If you select an asset or process or use case, we can always replicate faster. So it's always a matter of investing the right time to get to, through the assessment phase. Henry?
Yeah, I mean, just to kind of time bound that a little bit, we've seen anywhere from 2 weeks to about 8-9 weeks. I mean, that's once again, the 2 weeks one is not normal. That's depending on, most of tunes is already done, the customer's ready, and we can just kind of get them from the Pathfinder onwards. What we typically see is 8 to 10 weeks is probably a pretty good steady state operationalized.
Okay. Fantastic. Henry, Roberto, thank you very much. Great to have you give the presentation. I think it was well appreciated by the audience. We're getting a lot of comments through just thanking you, and actually had a lot of questions about the presentation being made available, which I guess I missed the start. So yes, we will be making the presentation, both the recording and PowerPoint, available to all attendees, and you'll receive that email later today. So thank you very much, guys.
Thank you so much.
Thank you, everyone.
Okay. Thank you, everyone. Bye.